Hold on, this computer. Hello, everyone. Welcome to our presentation on spoiler classification of Goodreads reviews, including user book bias and temporal trends. So our project is based on Goodreads book reviews with annotated spoilers. This project really came about from prior work based out of here at UCSD with Julian, where they were looking at spoiler detection from large-scale reviews. What are spoiler reviews? Essentially, if you have a sentence in a review for a book that is considered a spoiler, so it lets you know something that's going to happen in the book or an ending, it is given a binary label. If it has spoiler language in the sentence, it will go ahead and say it's spoiler or non-spoiler. The data set that we're looking at again has about 25,000 books, 19,000 users, about 1.3 million reviews. And really, what we know about the previous work based on that publication is that spoiler language tends to be really book specific. So it's not really across all around spoiler language. We also know that books and review authors have different levels of spoilers. So perhaps some users write more spoilers than others, and some books have more spoilers about them than others. And what's really interesting and what the paper found is that end of reviews often have more spoilers. So if you take the time to read all the way to the end, you might figure out something that's happening. Our question, though, and what we were interested in is, are there any sort of temporal influences on spoiler occurrences? Does the month of the review correlate with any sort of spoiler probability? Are there more months where we see more spoils? We'll see. Just to give you a big intro for our predictive task, where we're really interested in is if a review sentence is a spoiler or not. We're going to evaluate this using an accuracy and area under the ROC curve with the confusion matrix. For comparison, and then this is just to introduce it to you, we'll definitely go into more detail as we go through. But for the baseline, we're essentially comparing everything to the Wan et al. Paper that I presented. They looked at convolutional neural networks, support vector machines, and hierarchical attention networks. We're comparing it with a more simpler logistic regression, and then we're also adding some sort of temporal features to our logistic regression. In order to assess our validity and the model of our prediction, we're going to go ahead and compare it, our accuracy and AUC with the baseline. And then for our both the models that we're going to do, we're going to go ahead and create a look at confusion matrix comparing those two.
Thank you. So we have the data set that Wan et al. Published in 2019. As Daira mentioned earlier, the Goodreads review includes over 1 million reviews and many users, and lots of books are covered. The data set is broken down by Wan et al. Into sentences, and each of the sentences are tagged with spoiler tag. We'll see that in a few seconds. We also retrieved timestamps from the data set to answer our question. So if we look at one record, there is obviously the user ID and some information about the review. But there's also timestamp, and you can see in the review sentences, there's many sentences, and they have been tagged with whether or not it's a sentence that's considered as a spoiler or not. So if it's a spoiler, then it's tagged with a 1. So to account for some behavioral tendencies by the users, we want to account for that in our model. So we tallied up spoilers per user and also spoilers per book. Then we also looked at term frequency, inverse document frequency, TF-IDF. That is to weigh the importance of words in each sentence. And we also looked at document frequency, inverse item frequency, which looks for rare words. And that is important because usually a word that is unique to a book, like name or location, could be indicative that a user is about to start talking about spoiler contents. And finally, to answer our question, to see whether there's temporal influences on spoiler occurrences, we extracted month from the timestamp of each record. So to get started, we extracted all the records and stored it into Pandas data frame. And I will pass it on to Simone, who will share with you how we prepared the data set for the model.
Okay, as was mentioned previously, as part of our exploratory analysis of this data, we looked at user item biases, meaning some items, which are the books, may have more spoilers, and some users may be giving more spoilers. So if you'll look on the right here, we have a figure from the paper that explored this data set in terms of the percentage of spoilers per item and users. So item, which is the book, is in orange, user is in blue. And as you can see, there is a relationship between the specific book and or the specific user, meaning the person who's giving the review. Some are more likely to give spoilers and some are less likely to have spoilers. So we decided to use this as a bias in our model. So first we got a global spoiler bias, which was the overall spoiler rate, which was about 3.22%. So most of the samples in the data set are not sentences in the data set are not spoilers. And then we looked at the beta U, which is the user bias, which tells us how likely a specific user is to give a spoiler. And then we have beta I, which is the item or book bias. So this tells us how likely a specific book is to give a spoiler. So then other features that we computed from the data set were TF-IDF, which was a metric that we learned in this course, where it tells us the commonality of a word in a document. And so first it computes the term frequency, which is the word frequency, and then it multiplies this by the inverse document frequency, so the number of documents, or in this case, sentences we have in our whole data set, normalized by the number of documents that have the specific word. And then we also looked at document frequency versus inverse item frequency, which is what tells us if a word is more rare or book specific. So for a word, item I, which is the book, we calculate the book frequency given that word. And then we look for for each word, the item frequency, so how rare that word is for that specific book. And on the right, you can see that the item specificity, which is the document frequency multiplied by the inverse item frequency, is much higher in spoiler sentences than it is in non-spoiler sentences. So we're more likely to find rarer words and words that are specific to the item/book in the spoiler sentences. So both of these metrics are useful for our model. The DF-IIF is from the original paper that this dataset was provided, and the TF-IDF was, again, a metric that we had explored in class. And then finally, we also looked at any variability of spoilers per month. So as you can see here on the left, we have the total number of review sentences per month, and then how much of those sentences are spoilers per month. And so as you can see, there's like an uptick on the 5th month, which is May, and an uptick on the 10th month, which is October, which comes into play later on for our model. So for our machine learning problem formulation, the input that we have for our logistic regression model features, we have the TF-IDF, the term frequency multiplied by the inverse document frequency, the DF-IIF, which is document frequency multiplied by the inverse item frequency, so words that are specific to books, and then user item slash book biases. So if some books are more likely to have spoilers and if some users are more likely to give spoilers. For optimizing our model, and because we have many more sentences that are not spoilers than there are sentences that are spoilers, this gives us a class imbalance. So based on the original paper that this data set came from, we added a class weight bias during training. So for our non-spoiler sentences, the weight was 0.05, which was taken directly from Juan et al. And then for spoiler sentences, we kept it as 1. And then our next input was with the temporal model. So we did everything the same as with our original logistic regression model, but then added the temporal features, which gives us the month-specific coefficients. And we splitted our data set into train and test as 80 and 20%. And finally, our output would be if the sentence is a spoiler or has a spoiler or does not have a spoiler. So there were prior approaches for this model that were described in the paper. One of these was a convolutional neural network that was published in 2019, and it uses convolutional filters based on pre-trained text vector embeddings. And so this was very fast to train, but the con for this is that it depends on the original model's embedding quality. So if the prior embeddings were not trained well and or they don't capture enough information about book spoilers, then the model won't perform as well. The other model is a support vector machine, which is a linear classifier, and this was very fast and requires significantly less compute resources to train, but it requires engineering, meaning you have to be very specific in the parameters and features that you use to get good results. And then finally, the original paper's final model, which was SpoilerNet, which is based off of a hierarchical attention network. And the pro from this is that they used attention for contextual learning. But the con is that this requires a significant compute to train. So we had initially attempted to try and train a similar network to this, but because we didn't have the compute resources, our approach, we decided to go with a much simpler model, which is logistic regression. And so this was very simple, yet we had pretty effective results. The main con, though, is that it does not have the contextual learning from large language models like SpoilerNet does. So, yeah. Okay. So here is our code that we used to compute the features and train the model. This is what we did for getting the user item biases, which is exactly what we had gone over in class. So we're using an iterative method that continually updates the user and item biases. And with this, we had a learning rate of 0.01, a lambda regularization of 5, and we iterated this update 50 times. This is the code that we used for calculating the document frequency and inverse item frequency. So first we grouped the words by book and calculated the total documents by book. And from that, we counted how many books each word has, which gets us the inverse item frequency. And then we multiplied the document frequency by the inverse item frequency. We stored these values in a dictionary and then pulled those out depending on the contents of each sentence later on. So here is our one hot encoder for encoding the month feature. It's pretty simple. We had numbers of 1 through 12 representing each of the months. And then we used this only in our logistic regression plus temporal model, not in our just plain logistic regression model. And then finally, we combined the features. So I show the code for our logistic regression model, which just has the DF, IIF, TF, IDF, and user bias, user item biases. And the logistic regression with the temporal is the exact same features plus the one hot encoding of the months.
All right, so now that we have built our features for our two models that we're testing, and just to reiterate, one is incorporating the temporal features, and then the other one does not have the temporal features, but does have the biases as well. So here we can see in the first code chunk how we also take into account the class weights that were determined in the paper, given that our data set is highly skewed, and we want to let our model know that it should also pay attention to the positive class of spoilers, even though there's only about 3%. And so we can train our model for both what we are calling, our internal baseline, which is the model without the temporal component. And then also in the second chunk, we can repeat the same process, but this time taking into account the temporal features as well. And so, as we said, we will first compare between our two models. What is the effect of including temporal information in our ability to detect spoilers? And if we look at the accuracy, which is on the left side of our slide, we can see that it is actually slightly lower when we include the temporal component if we look at the overall accuracy. However, when we go into the class accuracy, which is what we care about, because of course, if 3.22% of your data set is the positive class, if you were to predict absolutely everything as negative, you would still have a fairly high accuracy. So it's very important to look at class accuracy as well. And we can see that including the temporal information only marginally improves our class accuracy for the positive class, which are the spoiler sentences. And also looking at the ROC-AUC, we can see that both models are performing pretty well with 0.88 without temporal and 0.89 when we add that temporal component. So we do see that improvement with the temporal component. But what we were really, and well, this is just a way to look at it again when we see the whole confusion matrices normalized between temporal versus non-temporal, and again, highlighting the importance of looking at class accuracy. But one thing that we were really interested in when we saw these numbers was that our approaches, which are here the bars in yellow and orange, actually perform surprisingly well compared to these more complex architectures that were used in the paper. So our approaches beat the support vector machine and the convolutional neural network, and they come fairly close to SpoilerNet, which is pretty nice, and it ties back to a lot of what we talked about in class with how a more complex model or a more complex architecture will not always give you better results, and simple can be good enough, which is something we're surprised to see. And then finally, just to tie everything together from what we did. So we knew that the spoilers were book specific. There was a lot of variation between books and review authors, and also, this tended to happen at the end of reviews. So we incorporated all of this information to create two different models, and one of which had a temporal feature, which was one of our main interests to see whether this was going to improve our ability to detect spoilers. And so looking into more detail into the temporal information, if we compute the coefficient for the model in which we incorporated the temporal features, we can see that there are certain months that are more informative or are more prone for spoilers to occur. February, March, May, October, and September, here highlighted in blue in the chart in particular. And we thought this was interesting because we know that authors sometimes tend to prefer publishing in October and September, so that might potentially explain why we see this pattern, as well as the beginning of the year, February, March. And there might even be something to say in regards with people wanting to read more at the beginning of each year and people who don't typically writing reviews in February when they're excited about their ability to be good readers. And so finally, this is one of a task in which we're more interested in being able to detect our spoilers. We don't care so much about potentially having false positives where, maybe just some reviews might be skipped. But it's very important not to have false negatives because then that would spoil the book for someone. And so here we show that our logistic regression models outperform the support vector machine and convolutional neural networks models from the paper that we used as a baseline. And even though they did not outperform SpoilerNet, they came surprisingly close given that they are simpler models. And our temporal data shows interesting variations of spoilers by month that might be explained by several patterns, although we have no way to prove that. And incorporating these features only marginally improved our class accuracy, but it did improve our class accuracy and AUC-ROC. And so finally, these are the citations of the paper and resources we used for this project. And if you have any questions, please feel free to shoot us an email or write them in the Piazza for discussion. Thank you.
Thank you, everyone.
Thank you.